who's going to talk about entanglement, entropy, and dilaton effective action.
So this is kind of a work in progress. I mean, okay, I'll tell you something which I know best, but there are some things which I don't know. Okay, so I'll be talking about this. Okay, so let me start with this. So I'll be talking about some connection between dilaton effective action and entanglement entropy. And this is actually motivated by like many works. I think Rob Myers is one of them. Like I think Myers, Smolkin, they wrote a paper on, okay, I don't remember all the authors, sorry. And then I think this was of course on a different thing. This was done by Komorgorski and Schwimmer. So this is the entanglement entropy part, I think, which was motivated by their work. And then we have this Komorgorski and Schwimmer. This is the dilaton part of the work. Okay, so the second thing is that this is about entanglement entropy in non-critical theories or massive theories. So okay, so let me start with 1 plus 1 dimension. So let me start with a theory, with a non-critical theory in 1 plus 1 dimension. So in 1 plus 1 dimension, say if you have a 1 plus 1 dimensional conformal field theory, we know that if we have an interval of length L, as Gautam has already mentioned, length L, then the entanglement entropy is given by this expression C over 3 log L over A, where A is an ultraviolet cutoff. Okay, and C is the central charge of the theory. Now, in so this was actually done by okay, say I'll say Cardi and Calabrese. And I think many people actually did this also. Okay. Now, so in 1 plus, so now in 1 dimension, so I take an system living on R1, okay, and I take an interval. So this is my interval here. Now, if you have a theory, say if you have a 1 plus 1 dimensional non-critical theory, of say some mass, there is a mass parameter which I call M, say, and if your subsystem is an infinite half line, then Cardy and Calabrese showed, sorry, Calabrese showed that the entanglement entropy of this half line is given by this expression, which is minus C uv over 6 log m times A, where this m is this mass and this A is again the UV cutoff, and this C UV, I mean it is clear from the notation that this is the central charge of the UV conformal field theory, which governs the behavior of this massive theory at small length scales. At high energy. Okay. Now, this is an exact answer, and this is quite useful actually. Okay. Now, okay. So, what I will do is that I'll mention that how they actually got this answer, and then I will get it in an alternative way. And okay. Now, the thing is that, but it's yeah. So, this is true in a two-dimensional theory, but you could ask, for example, what happens in a three-dimension or say four-dimensional theory, okay, or say six-dimensional theory or five. Okay. So, I will have nothing to say about the three-dimensional theory, but I will talk about the four-dimensional theory. Okay. Yeah. So, the standard way of computing, one of the ways of computing the entanglement entropy in field theory is, of course, to use the replica trick, okay, and use this formula at n equals 1. Okay. So, what this n means? So, you take your field theory, okay, so and so you put your field theory on a replica space, okay. Now, this replica space that has conical singularities with opening angle 2 pi n. It is with opening angle two pi n, and then the point is that, so for example, if you take your subsystem as an infinite half line in R1, then this replica space, the corresponding replica space is nothing but just a flat cone. It's just a flat cone with opening angle two pi n. So, you take something like this, okay, and the opening angle here is 2 pi n. Okay. And okay, I should mention this Fn is the free energy. That's the free energy of the theory on the replica space. On the replica space Fn, and F1 is the free energy on just the plane. Okay. Okay. So that's the definition. So you can actually get at this formula very easily, but I will not describe that. Okay. So okay, now the argument of Cardy and Calabrese for this 1 plus 1 dimensional non-critical theory was the following. They said that okay, so you have the free energy f of n, okay, and so this free energy depends on the mass. So let me just write it as f n comma m. So m is the mass, and then they said that okay, let me, if we differentiate this with respect to the mass, this free energy, what we get roughly, okay, I'll not be very careful about these factors, is this object, because this is changing the mass is equivalent to doing a uniform scale transformation, and the response is given by the integrated trace of the energy momentum tensor. So this T mu mu is where this T mu nu is the stress tensor. Okay. Okay. And what they did is that they actually computed this thing. So they and they essentially computed this object this object on the cone. Okay. And that answer what they got is actually given by, let me just, yes. So that answer, the thing that they got is like this. So that is just I think minus C UV over 24 pi times half times cone of our cone. Okay. So that is the answer which they got, and the proof is actually quite simple. So it goes exactly in the way you prove the C theorem in 2 dimension. Okay. So this let me explain. So what this object is. So this is the ultraviolet. So this is a massive theory. So there is nothing in the infrared, but they actually computed this object for a much more general case where, so if you have a theory which goes to the infrared, say which in the infrared is described by some non-trivial infrared CFT with central charge CIR. In that case, this expression is, they showed, is actually replaced by this, the difference of the central charges of the UV and the IR CFT. Okay, so we will get that, but let me just stick to the case where it's just a massive theory, so there is nothing in the infrared. Now this R is, so this object is the Ricci scalar of the cone. So you know that, for example, on this flat cone, R is 0 all through, but except that there is a singularity here, and that integrated object. So, this object you can integrate on this flat cone, and that actually gives you this value 4 pi times 1 minus n. Okay. Now, okay, so I would like to point out something is that the thing is that this okay, so that I will do later.
Where did the first factor 1 plus 1 over n come from?
Okay, I mean that actually, okay, so at the end of the day what you can show is that this is actually given by the trace of the stress tensor of the UV conformal field theory on the cone, and then that you can compute. So, you can do this map, okay, that maps it to the plane, and then you have a Schwarzian factor which gives you this 1 plus 1 over n times 1 minus n. So, I have just written in this form so that it is clear that, yeah, so it has something to do with trace anomaly things. Okay. Yeah. So, for the cone we have this expression. Okay. So, that is all, and this is actually very, like, the proof is quite simple. I mean it goes exactly in the way the C theorem is proved, but the thing is that, I mean, as we know that we do not know, for example, how to do it analogously in 4 dimension or say 3 dimension. So, this result cannot be extended to higher dimension, because we do not know what is the analog of the proof of the C theorem, in like the way we prove the standard way of proving that cannot be extended to higher dimension, because there are too many, yeah, I mean there are too many co-oscillators involved. Okay. So, how am I doing with time? Oh, that's great. Is it clear? Okay, let me just. Yeah. So, okay. So, what I will do next is that in the next 10 minutes, so I will prove this thing in a different way, and which can be extended to higher dimension. And this is possible because of a recent, not quite recent, but yeah. So, let me now come to the dilaton. Okay. Now, dilaton, okay, roughly let me tell you. So, dilaton, I will treat this just as a background field. So, just think of it as a background field, and the role of this thing is that this couples to the trace of the stress tensor. Stress tensor of the theory of the field theory. Okay. So, the coupling is something like this. So, let me introduce some metric. So, it is a scalar field, okay, thing like this. Yeah. Okay. So, the thing is that so like we do in the standard thing, that if we want to compute any correlation functions or like a 1-point function, 2-point function, what we do is that we couple the theory to a field, to a background field. It is exactly like the coupling which we do in the scalar, say in phi 4 theory or in J of phi. So, J is now, I will call this tau, and this phi, the operator which I have, is just this trace of the stress tensor T mu mu. And so, as you, yeah.
G is the source.
Yeah.
It doesn't have any equation of its own. So
Yeah. So, tau, so if you just think of it as a background field, it also does not have any, I mean you do not have to impose any equation of motion for the dynamic. Yeah. So, okay, so the standard thing of computing the this trace of the stress tensor will be to compute the okay, like in field theory, what we do is that we compute this object z of j, okay, right, something s, okay. So here what we compute is this object, say, let me just write it as. So here just we compute this object w of tau, okay. So if we know what is the effective action of this w of tau, then that actually gives us the trace of the stress tensor. So it's simple. I mean, there is no, as such, there is no problem. Okay, so yeah. Okay, so now the question is that okay, so now what we have to do is that we want to compute this object, which is this integrated stress tensor on the cone. Okay, so what we need to know is that what is the effective action of the dilaton on the cone. Okay, so once we know w of tau on the
Just drawing parallels between them, you are going to integrate over T mu. So what is the role of T5, the functional?
yeah, so these are all the fields of the theory set. Okay. Yeah, so I mean this is just a standard like you have, like, for a scalar field T mu you will have some form, right, something, and then so this T mu mu is some function of phi, let's say. Okay, so it's a kind of a composite object. It's not just j of phi, and it's a source. I mean that's what you do usually. Like if I have some operator O of x, I could formally couple it to some source. That's yeah. So O of x is built out of the fundamental fields. Okay. Right. Okay. So this effective action w of tau, so that can be computed. Some terms of it can be computed very easily, but not all. I mean, you have to do a hard work, but I think that's true in all cases. Yeah. So let's look at some of the terms which can, okay, which I will call some of the universal terms. Okay, it's not the universal in the sense of the, for example, in 2 dimension we had a structure like this, that we had the entropy going like C over 3 log L over A, and this is a UV divergent quantity, but since the coefficient of this log is C over 3, since it's a logarithmically divergent quantity, the coefficient of this object, I mean that does not depend on what ultraviolet cutoff you choose. So that's a universal quantity, but this universal is something which I'll explain. So these universal terms, they actually follow from the anomaly matching between the UV and IR in the presence of the dilaton field. Okay, what I mean by this is that the total anomaly, the total trace, okay, sorry, this is the trace anomaly. Okay, so the total trace anomaly of the UV CFT is actually the anomaly which comes from the dilaton effective action from W of tau plus the anomaly of the IR CFT. Okay, so this was actually argued by Pomorgotsky and Schwimmer. Okay. Now, this actually puts strong constraint of what your W of tau can actually be. Okay. Now, let us look at some of the terms which are allowed by this. I mean, we just follow from this condition. So, yeah. Right. So, right. So, if you now write down the dilaton effective action on the cone to get, so in place of W, okay, let me change it to F because I am using the F. Okay. So, in 2 dimension on this flat cone, just a flat cone, so there is nothing, there is no scale, nothing involved in it. So, that you can write okay, I will say okay. Now, this tau, okay, just let me mention one thing. Since I am interested in just this integrated trace of the stress tensor, so I have taken tau to be a constant. Okay, but it does not really matter. I mean, you could start with a non-constant tau, and then you could actually set tau constant at the end. Okay, it's a constant background dilaton. Right. So, this is the, so this term, so this part of the thing actually follows just from this anomaly matching, and in this case what happens is that, okay, so let us look at this object which is n equals 1. Now, okay, the role of this difference that, so you have f of n and then you are actually subtracting n times f1, and the role of this n times this subtraction is that roughly you can say that this is actually the contribution which comes purely from the conical singularity. So, this actually cancels, I mean once you subtract n times f1, this cancels all the bulk contribution of the free energy. Okay. From the okay. So, I mean that is quite intuitive also, because you will expect that the bulk free energy will not contribute anything, and whatever you will get is the entanglement entropy will come only from the conical singularity part. Okay. Now, you could have other terms in this dilaton effective action, but here the things simplify just because you do not have any other scale in the problem. I mean, if you for example, if you take an interval of finite length L, in that case you will have the finite size corrections to it, and which will actually change this thing. Okay. So, now once we have this free energy, the dilaton effective action and this difference that actually follows from this fact that the variation of this object when you add it to this infrared CFT, it exactly cancels the anomaly of the infrared CFT and gives you back the ultraviolet CFT. So from here, you can, so the trace of the stress tensor I will define just as in this way in my convention is sorry, so that is T mu mu, okay, and this T mu mu is just given by on the cone is d tau. So you get this expression which is so you have a tau here which goes away, and then you are left with this term. Okay. And this is precisely the answer what Cardy and Calabrese got. Now, let me mention it very clearly that if you take an if you have other dimension full quantities in the theory, for example, I mean if you have interval of length L, then there are other terms in the dilaton effective action which will contribute to this and which will give you the finite size corrections. But since I am just considering an infinite half line, so those corrections are not there, and you get back this answer by Calabrese and Cardy. Once you replace this thing, I mean they also prove that. Okay. So once you get this, then you can use the same argument that they used, I mean this equation, and then that, so that gives you this. So now, since using a replica trick, we know that this entanglement entropy okay, so you can take the differentiate with respect to mass, and then that gives you the free energy. So you know this from there, and that gives you this answer. Finally, if you write everything correctly, what you get is this. So that's what Cardy and Calabrese actually got, that this quantity okay, so if you don't have any CIR, I mean if it's just a massive theory, you can just set CIR equal to 0 and get back whatever is written in their paper, which is and if you have a non-trivial infrared central charge, the answer which you get is so this LIR, that's an infrared cutoff because of the infrared divergence of the IR CFT. Okay. Now, you can also compute the finite size corrections if you are hardworking. So Cardy and Calabrese actually did that for finite for massive scalar field for which the action is this, and you get lots of interesting things. So you take this action and compute the entanglement entropy for length L. Okay. Okay, and the thing is that as L goes to infinity, since it's a C equal to 1 theory, what you get is minus 1/6 log m times A. I mean, that can also be checked explicitly. Okay. Okay, so that's the story of the 2 dimension. So what I wanted to convey to you is that you can actually derive this thing in a way which doesn't depend on whether you are in 2 dimension or not in 3 dimension, but in 4 dimension. Okay. But in 4 dimension, something else will happen. I mean, you always have scales in some sense in the theory. I mean,
in the answer, there were terms that look like log of something square times some quantity. I mean, log square, not just logs. And those coefficients you would call universal, right? So
log square.
yeah.
How?
Suppose
Where do you get?
Dimensional analysis, I mean, couldn't I have things that look like log of this one?
You mean log of log something square?
Yeah.
So, I mean, if you have log something square, and then if you have log together, then this is a universal term because you could actually change this log by this. So, I think that's true.
Is it easy to understand why these don't appear?
Log square, I think, appears if you have some kind of yes. I mean, if the boundaries have like what today? I mean, there are sharp edges, something like this. Yeah, probably that's true. Yeah, but yeah, I mean, so if you have both log and log square, then the log term is not universal because you can change that by changing the log square. Yeah. Okay, so. Yeah, so this, of course, this method cannot be done in 3 dimensions. The reason is that there is no trace anomaly in 3 dimension. So, how much time I have? 20 minutes. So good. No trace anomaly in 3 dimension. Okay. So 3 or any odd dimension. Okay, so you cannot get it in. I mean, you cannot get. I mean, for example, the result of 3 dimension or 5 dimensions in this way, but you can. But this thing actually works in all even dimensions. All even space-time dimensions. Okay. So, let me go to the next non-trivial dimension, which is 4 dimension, and which is also the interesting one. Okay, so in 4 dimension, of course, we have trace anomaly. Okay, we have trace anomaly. Okay, and let's take a theory of say some mass m. Okay, and okay, so I mean, there can be varieties of entangling surfaces in 4 dimension. So let's take any compact surface with spherical topology. So it will be something like, say, this is a spatial dimension. Let's take something like this. So there is no cast like a thing. It's just all smooth. Okay. So this is my entanglement region. I'll call A. Okay. And the boundary I'll call del of A. Okay. So I want to compute this thing. Okay, so one can actually do it in the same. Okay, there are 2 things one could actually compute. One is this entanglement entropy, or what people many times compute is this renormalized entanglement entropy. Okay. So this renormalized entanglement entropy, that is a finite quantity. And that is also claimed to be the, I mean, if you take your del A to be a sphere S2, then this renormalized entanglement entropy is also become your C function in 4 dimension. Okay. So, okay, so let me compute this. I mean, one could actually go back and forth between the two. Okay, so it's the same way that we actually compute this thing. So we compute this object. So you have a mass. I have this entanglement entropy. Again, I use the replica trick. Okay, sorry. One thing which is very important, which will actually play a role in 4 dimension, is that in 2 dimension. Okay, so when you are writing this dilaton effective action, okay, so you have to, the universal term of the dilaton effective action. Okay, say let's talk about the 2 dimension. So there you have to know what is the conformal anomaly on the cone. Okay, so you have to know what is the conformal anomaly of a CFT on the cone. Okay. Now this expression is actually not the standard expression. So we know that in a in a CFT, in 2D CFT, we have this. Okay. I mean up to something. This is actually C times R. Okay, where R is the Ricci scalar. Okay. So you will expect that on the cone, this integrated anomaly, this T mu mu, that is just this object CR on the cone, okay, and that gives you 4 pi C times 1 minus n. Okay, but that's a wrong answer. Okay, we know that. I mean, it's going to give you the wrong answer. Now the correct answer is this thing actually, that if you compute, if you put a CFT on the cone, and then what you get is C times 1 plus 1 over n. Okay, so this was actually showed long ago. I mean, quite a long time ago by Cardy and Peschel. I think in sometimes, where they pointed out that if you put a CFT on the cone, you don't get this naive expression, and you have to use this, and this actually follows simply from this map. You could prove this, and that gives you this. I mean, this is essentially the scaling dimension of the twist operator. Now, this is important because we don't know what is the same thing in 4 dimension. Okay, so how are you going to write down the dilaton effective action in 4 dimension unless you know what is the exactly what this thing is? Okay, so what I will propose is the following thing, that if you look at this expression, let's see. Okay, now this object, if I define some, sorry, this is half actually. This is half, yeah. So if I define this effective central charge like C of n as half as C by 2 times 1 plus 1 over n, then as you can see, C of 1 is actually the C, which you get this thing, and the C of n has an expansion. Okay, in it's like C plus something times 1 minus n and plus something time 1 minus n square. Okay. So, now if you now this root g r on the cone, that actually gives you a 1 minus n. So, if you multiply these expressions by these two, what you get is so c of n times this root g r, that has an expansion like this. Okay. Now, these terms actually do not contribute if you want to compute the entanglement entropy, because entanglement entropy depends on I mean, you have to differentiate this with respect to n and then set n equals 1. So, these terms do not contribute, and so if you are very close to 1, that is your n is something L is something 1 plus epsilon, with epsilon very small. So, what one can do is that you can just replace this with the standard C. I mean, if you are just interested in computing what is the entanglement entropy. Okay. Now, that is important. So, for example, in 2 dimension, we also got the correct expression for what is called the Rayleigh entropy, but we will not be able to do that in 4 dimension. Okay. In 4 dimension, what I will get is only the entanglement entropy. Yeah, then you get a wrong answer for this. No, because the thing is that like on the regularized cone, this object, I mean, if you put this conformal field theory, this object is fixed, right? This is just root g r. So this will depend on some cutoff a, I mean, which is your regularization parameter. Okay. So you have this smoothed out cone, something like this, say. So you have this original thing, and say this is something like this, the small parameter which you actually get here. And since this is a smooth geometry, I mean, there is no reason, okay, you have to have this thing true. Okay, and all the dependence on A will actually come from this, right? Whatever you get. So if you as you take A to 0, you actually get back this on the cone. Yeah, so a smoothed out cone usually gives a wrong answer. Yeah. Right. Yeah. Yes. For the entanglement entropy, it doesn't matter if you. Yeah. I mean, if you can make sense of it. I mean that n is a non-integer. So yeah. So there are. I mean, okay. I mean, there's no. Okay. I mean, it could be wrong also. I mean, that's the thing. But yeah, but in all the examples, it turns out to be the right thing. That I mean, you can take a smoothed out cone for computing the entanglement entropy. Yeah. Right.
Isn't that what Leibovitz and Marasana also more or less do, except that they define the subtraction in a clearer way?
Yeah, but they are computing entanglement entropy, right? Yeah, right. So you can do that on a smoothed out geometry. Yeah, but in general, I think in field theory, it will. I mean, if you want to compute this log trace row to the power n, you can't. Yeah, you can't actually start with it.
Yeah, it's just a subtraction. You know, whether you use an integer n in the subtraction,
Yeah.
or a fractional n in the subtraction.
Right.
That's what their description was there. That was not just the smooth n way to one limit. Right?
Yeah. So here, yeah, but the thing is that here, of course, the thing is what I'm saying is very simple. I mean, the thing that he asked actually is that, I mean, if you take a smoothed out cone, by smoothed out, I mean, say you replace it with some hyperboloid, and the distance is something like a. So a is the regularization parameter. Now, if you put your CFT on this smooth geometry, then you have to have this, right? It's a smooth geometry, so there is no reason for that. Now, all this A dependence will come here, right? So, as you take A going to 0, it has to give you this 4. So, but that's not the right answer. So, it was actually also pointed out by Cardy and Peschel, in their this 86 paper. Yeah. Okay, so let me just go through it quickly. Yes, so 5 minutes, 10 minutes. Okay. Right. So, and then, okay, you do the same thing. You take the derivative with respect to mass. Okay, so I'll also mention one more thing. Okay, so let me also mention. Okay, no, let me first do the 4-dimensional thing, and then this actually gives you this object. So, you can compute this thing again in the same way. Okay, so now we know, so this is actually, okay, it goes in the same way, except that I have to write down the anomaly expressions. So, you can write by the same anomaly matching condition, the universal term in the dilaton effective action. So, that's one of the terms. That's not all. There are an infinite number of other terms which are there. So this thing for a constant background field in 4 dimension has this form. So, this is evaluated on the cone, okay, and then this W square is the Y square, which is and this E4 is the Euler density. Plus R square. So, these are evaluated on the cone, but subject to the constraint. Now, okay, so typically actually one should replace this whole thing. There will be some function of n, which I don't know what it is. Okay, so if you know exactly what this n is going to be, so this n, it's similar to what we had there, like half into 1 plus 1 over n, and but we saw that in order to compute the entanglement entropy, we can actually replace this thing with just standard central charges, okay, and okay, so I'm also considering a massive theory. Let me get rid of this thing, okay, and so from here you can easily read out what the expression in the same, exactly in the same way as in the 2 dimension. So, you will have this term which will you will have a term which is, because so you have the tau here, so df d tau gives you what your trace of the stress tensor is, and then you get this expression. You have the CUV times this whole thing, this actually evaluated. So let me write down for a sphere. So let us take, so so the full expression is actually known what it is for any geometry, but if you take, for example, if you take this to be a sphere, okay, then the thing actually simplifies, and what you get is just, okay, let me write it in this form as okay. So this is one of the terms, this is one of the universal terms which you will have in the entanglement entropy, and for the sphere, when the entangling surface is a sphere, and this term is actually exactly similar to what we had there, which is CUV over 6 log m times a. So this is in 4 dimension for a sphere. So I haven't written down an equality sign because this is one of the terms, and this is a universal term, and this is in 2 dimension for an infinite half line. Okay. So you can see that this same so you get the same type of expression also in 4 dimension. Okay. Now in 4 dimension, if you are just interested in the universal terms, by that I mean the coefficient of the logarithmically divergent terms in the entanglement entropy, by that I mean the logarithmically divergent terms, so in 4 dimension, it's okay. One can just analyze the dilaton effective action and show that there is one more term which say for which is of course true in any A, can be written as for when del A is a sphere. Okay. So there you have this term which I will write plus some constant, let me call it C1 times m square Okay, I don't have time to show that, but by analyzing the non-universal and non-universal in the sense of the dilaton effective action, one can easily show that this is the only possible other term which can occur in the universal term, in the log divergent term of the entanglement entropy. And this C1 can be calculated from the dilaton effective action. I mean, you just compute the effective action in the standard way. One way to, okay, I mean, if you assume that, okay, I mean, you could do it near the fixed point, I mean, in a conformal perturbation theory. I mean, that is one, that is one practical way of doing it. You could. Yeah, but the thing is that that you can write, but the point is that you have to know what is the coefficient. I mean, this is a dimensionless number, and that, I mean, constant. So that is not determined by any Weyl invariance. Okay.
Radius dependence comes only in the non-universal. It is not the universal term. They don't depend on the radius of the sphere.
Yeah, actually the point is that here the radius dependence is kind of tricky, because the point is that I think what one could do is that I could as well replace this m with say some r, okay, and then you add a finite term to the entanglement entropy. So that's so. I mean, in non-critical theories, I think that is kind of. I mean, if you have like many scales, then what you call your. So what I should write is that this quantity actually goes like log a, and then you can put your constant. I mean, whatever the length scale you choose to put actually. Okay. Now, okay. So I'll just so this can be done in any dimension, and this the best way to compute this C1 is in conformal perturbation theory, because then you could get, for example, what is the dependence of C1 on the dimension of the operator, which is actually perturbing the ultraviolet CFT. Okay, and I think this also matches with the ADS CFT answer that that this structure also appears in the conformal field theory, and it stays there even in the non-conformal field theory, and that is explained by this anomaly matching. Okay, so yeah, so yeah, so just oh no, that is just for simplicity. For example, if you take a cylinder, okay, so this A will be replaced by C. And for example, if you take, okay, I mean, I think Myers and collaborator, they computed, so they, for example, consider this spherical waveguide geometries. Okay, so there, for example, if you do it, what you get is this number. So you can get all sorts of things here. Okay. So yeah, so that of course, so you have to just evaluate this expression on whatever, on squashed cone or whatever is your favorite regularization is. Yeah, so I'll just mention one thing, which is the last thing is this thing. Is that so one of the ways that Cardi and Calabrese actually computed it in 2 dimension, and also Cardi actually recently computed for free field theory. Okay, not recently, but yeah, I think 2010 probably. So he computed in 4-dimensional theories in massive scalar fields actually. So the way he computes is this following thing. So you compute what your Z is. Okay, and then what he computes is actually this object. That's his favorite object, I guess. Log Z. Now, this is exactly what I am doing actually, because this object, I mean, different. The reason is that you could, for example, I could replace this action, this free energy, with this. Think just yes. Okay, so this is the way to couple the background dilaton field to the scalar theory, and if you compute this m square ddm square of log Z, so that is actually equivalent to computing the dilaton effective action at tau equal to 0. So that's exactly the same thing. So that's so what is actually being done in the standard literature, that they secretly, I mean, they compute these effective action. Only thing is that, okay, I mean, they write it in this form as m square ddm square of log Z, but this can also, I think there will be a half factor here. So, but this can also be written as the dd tau of the dilaton effective action evaluated with tau equal to 0, and you could actually set this tau as a constant. So space-time, it's a constant background field. Okay, so this I think is a systematic way to compute the entanglement entropy in non-critical theories. And yeah, and the point is that one can, of course, I mean, compute all the finite size corrections and the practical way to compute this thing will be to use conformal perturbation theory if the fixed points are close. Yeah, so I think I'll stop here.